Better? Yes? Okay. So let me know if it fades out at some point, and I'll try to adjust the microphone. The other thing, can everyone read this? I tried to write large enough for the people in the back row to see, but if at some point I lapse into smaller writing, please remind me, and I'll try to go back to larger characters, the visible characters. So I've written the title of the talk there, the quantum measure and how to measure it. It's really a talk about a recent result obtained mainly with Alvaro Mosota, who was a master's student at the time at Perimeter Institute, about how to measure the quantum measure. But what is the quantum, and I should say that in a certain sense, this result, this protocol that he worked out, or that we worked out together, constitutes, in a certain sense, a new kind of measurement or a new kind of observable with a correspondingly new kind of measurement that one can actually do in the laboratory. And maybe we have someone who actually will do something in the laboratory like that. And so it's perhaps in the same sense as the, I hear that this sort of fades in and out. Is that, it's okay. In the same sense that weak measurement is a different kind of protocol, which we heard a lot about in the meeting so far. This is, you could view as yet another kind of protocol that goes to observables that are beyond the ones that are usually considered in ordinary, let me call it ordinary quantum mechanics. Or sometimes I'll refer to it as Copenhagen-Luder's quantum mechanics. I'm not sure what to call it because I don't think it's exactly the Copenhagen interpretation, but it involves ideas like collapse of the wave function. This is the familiar thing anyway. So for short, I'll refer to that as ordinary quantum mechanics. And I'd say that this idea of observable, or beable if you prefer that word, goes beyond the kind of ideas of observable that one normally encounters in ordinary quantum mechanics in such a way as hopefully to be useful for, on the one hand, quantum gravity, which, as our chairman mentioned, is probably my main interest in physics, and on the other hand, for quantum foundations. So before I get started, let me just say a couple of words about why I'm interested in this way of formulating quantum theory from the point of view of quantum gravity. So I think it's, in a certain sense, fair to say that quantum gravity has something to offer to, this is quantum foundations. Quantum foundations means, of course, well, in some sense, it's the title of this whole conference, I suppose, but it's obviously the attempt to understand the quantum formalism more deeply than one does when one thinks of it as just a recipe for computing the probable or the probabilities of different outcomes of laboratory procedures. In fact, if I were to try to characterize the task of quantum foundations in one sentence, I would say it's the it's the attempt to understand to what reality does the quantum formalism refer. So that's quantum foundations. Now, why does quantum, I want to claim that quantum gravity has something to offer quantum foundations, and conversely, quantum foundations has something to offer quantum gravity, and sort of at the nexus of this relationship is some sort of generalized path integral, which we call the quantum measure, and the associated formalism set of ideas, which one can call quantum measure theory. So why do I say that quantum gravity has something to offer quantum foundations? Well, I won't go into a long discussion because this is not on quantum gravity, but very arguably, and people have made this argument going back to the quite early days thinking about quantum gravity, that quantum gravity needs histories. It needs to think of the world in terms of histories. That is to say, in terms like the path integral uses, as opposed to the idea of wave functions, operators, and well, collapse of the wave function, and the Schrödinger equation. So the Schrödinger equation should, in some sense, from the point of view of quantum gravity, is not a natural thing. The wave function is not a natural thing, all because those things are tied essentially to some sort of moment of time, more or less explicitly in formalism, a Cauchy surface, if you like, and that's unnatural for gravity. It does violence to general covariance. A more technical way to say that is that the observables, the covariant quantities that you can talk about in quantum gravity and meaningful questions in gravity, let alone quantum, the meaningful questions that you can ask all are global in nature, and they don't fit well, therefore, with idea of a state and a moment of time evolving in time. They do fit well with the path integral. Just to mention one example to think about why I'm saying this, and I could utter the words diffeomorphism, invariance, blah, 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 but instead of that, just think about a black hole. Suppose you're interested in whether a black hole has form. If so, how big is the horizon? Do we see it shrinking according to Hawking radiation? How would you describe any of that in terms of initial data, just the metric at a moment of time? You can't. You need access to the whole space-time. And that's what a histories formulation gives you. That's what the path integral gives you. So I claim that quantum gravity has something to offer. When I say it has something to offer quantum foundations, what I mean is it offers us the perspective that it's better to think in terms of histories. And you might, if you're interested in quantum foundations, think ahead that what are you going to use it for? And then you would say, let's think in terms of histories, which is not, unfortunately, the way that very few people practice quantum foundations. On the other hand, I think that quantum foundations has something to offer to quantum gravity. Quantum gravity needs, or let's say more cautiously, may need to solve some of the problems of quantum foundations. And why is this? Well, because the whole framework, the whole conceptual framework of something like what I call the Copenhagen-Lüders point of view involves a laboratory, involves an external observer, right? An external agent who's able to prepare things, make controlled measurements, repeat them over and over again. None of this applies to what's presumably going to be the main field of application of quantum gravity, which is quantum cosmology, right? In the early universe, there were no observers. If you're doing cosmology, there are no external agents. You can't get outside of the system, and you certainly can't, in a controlled way, create new universes or new portions of the universe, at least so far, and study them. So we need a way of thinking about the quantum world directly without putting us at arm's length and having to think of it in terms of laboratory-based observables. There's also a technical reason, I'll just say it in words. It has to do with the causal set program, which was mentioned, that I won't really be talking about today, which is that the notion of, well, as the name causal in causal set even indicates, the notion of relativistic causality is somehow supposed to be crucial, and most people, many think it is crucial in gravity and quantum mechanics in general. And there's a certain notion of causality which we've developed in the classical stochastic setting, which we would hope to generalize it to the quantum system, and that would be a stepping stone or an important clue towards formulating quantum gravity in the causal set language. So if you're going to understand causality, you want to understand which events cause which. So a key idea here is event. You want to understand which events cause which other events. To give that meaning, you really need to be able to talk about the events. We're not talking about which observation causes which observation, but in the real world, which events cause other events. So there's a hope that if we sort out this quantum foundations issue, then it will give us a way to talk more directly about causality and therefore be of use to quantum gravity. So that's kind of my little sermon, and it's my little apology, not in the sense that I'm ashamed of it, but there's my apology for why I'm interested in this kind of formulation of quantum gravity. So so when I say history's formulation, I really mean, can we do quantum theory with something like the path integral and nothing more, none of this other apparatus that one is used to assuming when one does quantum gravity. Is there a question? Or I guess maybe just an echo. Okay. So so can people over there, if I write here, can people over there see what's here? Yeah? Okay. So give a brief plan of what topics. So the first, I keep uttering the word histories, and I will be uttering the word events very often, so I want to define what they are, and I'll do it in relation to a particular model system, a very simple model system, which I'll call the two-site hopper, which is just, well, I'll give an explicit optics lab type of realization of it in terms of beam splitters and photons. You'll see what it means, but it's basically just some object, let's call it particle, which can, at discrete moments of time, hop back and forth, or not hop back, or stay where it is, as the case may be, with a certain amplitude. It's a kind of prototype for the path integral. And in general, and it's the simplest case I know where you can talk about a path integral. And everything is finite, you don't have to worry about thorny mathematical problems like if you do a continuous path integral for the Schrödinger equation. So that'll be sort of the arena for most of the discussion. So I'll introduce the idea of histories and events, especially in relation to that. Then another tenet of quantum measure theory, or let's say it's just a consequence of taking quantum measure theory seriously, is that quantum mechanics from a certain point of view, namely from this point of view, is best thought of not as a generalization of Hamiltonian mechanics, which of course it is in a certain way, but it's better thought of as a generalization of classical stochastic processes. And the paradigm, or the sort of most venerable example, I think, of a classical stochastic process is a random walk. So I want to say a little bit about it to show that all the same concepts, especially at the kinematical level, all the same concepts apply to the random walk that apply to history's formulation of quantum mechanics. So it's useful, I think, useful on the one hand to introduce some of the terminology, and on the other hand, just to get a feeling of what a history's approach is. In the case of a random walk, we'll see that a history's approach not only deals with the analog of the Schrödinger equation, which would be the diffusion equation, or whatever it's called in the discrete time case, some name, I don't know, Fokker-Planck. Anyway, it has different, I'm not quite sure what the name that people have given it, but the equation that tells you how the probability distribution, the random walk is, of course, on the integers, tells you how the probability distribution evolves with time, but it's actually probabilities for events, or classes of whole histories. It's something of a more space-time character. So, and there's probably, I shouldn't do this, but there's some very beautiful, very simple results that one can prove with a random walk that you can find in many textbooks, but I just want to go through them to show how how the random walk deals with a problem that many people have grappled with in the quantum context, which is called the problem of arrival time, or in the case of stochastic processes, it's called the problem of first passage. So it's like, if you release a particle here, what's the probability, and if it arrives over here, what's the probability distribution of the time at which it first arrives, and how likely it is to arrive after 10 steps, 11 steps, 12 steps. This can be computed exactly. Maybe I'll just review it a little, rush through it a little bit, just so to feel that you really have your hands on what a history's theory is. And then we'll see the differences that arise when you go to the quantum case, which in some sense are not that big, but of course in another sense are very, very dramatic. Then I'll talk about the path integral and the quantum measure. This is the quantum measure. That's which I'll give the name mu symbol because that's a traditional idea for a traditional symbol for a measure, at least for a classical measure. If there's time, which I sort of seriously doubt, I would say something about some of the antinomies, what I call antinomies or paradoxes that arise in quantum mechanics that make it difficult to interpret it. I think there's one of them that I call the three-slit antinomy, which is actually, I think you saw it already. It's isomorphic to what some people call the three-box paradox, usually discussed in the context of weak measurements, but it's basically the same thing. Then I want to stress one thing. I see it's getting smaller already, but the completeness of the path, what I call the conceptual completeness of the path integral. By that I mean, to exaggerate maybe slightly, is that everything that you can compute with the path integral. The important point is that you can compute all the Born rule probabilities without ever mentioning Schrödinger equation or projection operators or collapse of the wave function, just directly from the path integral. Then I'll introduce quantum measure actually in a couple of stages of increasing generality, ending with an abstract axiomatic framework for quantum measure theory, analogous to the Kolmogorov framework for classical measure theory or probability theory. And I'll mention the general form of the quantum measure for a unitary theory. So one might think, and I do think that quantum gravity will necessarily go beyond unitary theories, but all the examples we have that we understand well so far are unitary or open. And I should mention this also, open systems. So for open quantum systems, which you've heard a lot about again, which are part of a larger unitary theory, of course, evolved non-unitarily and generally not with Markovian evolution. All of this is handled extremely naturally by the path integral and by quantum measure theory. So let me mention that also to make contact with some other things that have been discussed, have been sort of leitmotifs of the conference so far. Then I want to, maybe someone will be able to suggest a good word for this. I don't have it. I call them events distributed in time. The thing that makes the path integral or quantum measure theory somehow go beyond the ordinary Copenhagen-Luders framework is that it deals with a more general kind of event, which is the kind of event I was talking about in relation to quantum gravity, like events relating to black holes, for example. And I call them distributed in time. In other words, they don't just ask what's happening at some moment of time. They ask about, if you like, correlations or more complicated questions about what the object, what the path, or what the system in question is doing. So I don't know. I've called them non-instantaneous events or events distributed in time, global events, space-time events. Maybe someone can suggest a better name when you see a little more what we're talking about. Then all this is by way of introducing the general framework, and then I want to describe the very recent new result in the last couple of weeks or so. There's a paper appeared on the archive within a couple of weeks ago, 3 weeks ago, something like that, which tells us, so for each event there's a measure, we'll get to this again, but for each event there's a measure which classically you could have thought of as the probability of that event happening, and quantum mechanically is something more general. And it's not been clear until this recent work whether this quantum measure, although it plays a central mathematical role, in the formalism, whether or not it could be given a direct experimental meaning. And the result is that yes, in a certain sense, it can. And so that's what I want to conclude with. So how to measure mu of E, and we'll do it. So the simplest case is an event, as I'll define it, is a set of histories. So by this absolute value, I just mean the number of histories in the event. So when the number of histories in the event is 1 or 2, you can write the protocol very explicitly and see exactly what's going on. So I'll do that, and then I'll finish, if we get that far, by describing the protocol in general, how to measure the measure, how to experimentally ascertain the measure of any event, no matter how many histories it contains. We'll see that it will have, in this general, and even, well, in both of them, the technique will be to couple. Maybe it's worth mentioning that when I first started to work on this, I thought that it was going to be ideally, that weak measurement techniques were going to be ideal for it, but it turns out what Alvaro discovered is that we can do it all with ordinary strong measurements, and still is, we don't need to think about the weak class of measurements. So, but the ancillas will play a crucial role. They will be coupled to the history. History, when I say history, think trajectory of the particle. They'll be coupled to the history in such a way as to somehow, so to speak, know what the trajectory was. And then they must be coupled to each other in a clever way, and ultimately to a pointer or a counter, we call it. I'll call it a counter, which will either click or not click. And whether it clicks or doesn't click is, in some sense, an indication of whether the event happened or did not happen. And the probability of it clicking will be, it's a little more subtle than the usual situation. The probability of clicking will not be the measure, but it will be proportional to the measure by a simple factor, a known factor. In fact, just the factor of the cardinality of the event. So that if you experimentally determine the probability of clicking, then you will have measured the quantum measure. So that's the sense of the title. One can go further and then ask, which I almost did ask just a moment ago, if the counter clicks, does it mean that the event really did happen? I think I'll just finish by raising that question, because that opens the whole can of worms, the quantum foundations. If you say, did it really happen, then you have to be prepared to talk about things really happening and not happening. And that's not a stage that we've reached in the quantum foundations, but one can make a strong case that it's plausible to say that indeed it did happen, so that this experimental procedure I'll describe acts as a kind of filter or detector for a given event, the event for which it was designed. Okay, so let's step back a little before plunging into the formalism. Let's step back a little bit and just think about quantum mechanics in general and what makes it different from classical physics and what makes it the same in the way that I'm claiming that it is the same in dealing with the same kinds of objects, histories, and events. Let me get your opinion, just take a few suggestions about two questions. What is quantum mechanics about? And then, I'm asking this because I'm going to give a list of possible answers and say, which answers the ordinary view might be and which answers the history's view would be. But there's sort of two questions. What is quantum mechanics about? And what makes it different? How does it differ from classical physics? So let me take, I don't know, a few suggestions just to see what people might feel about it. So what would you? This is a little vague question. What is it about? If you don't have an answer, I could suggest a sort of drop-down list of answers. So, but anyone, what do you think? Yeah. Well, quantum mechanics is a whole theory or a whole class of theories. But if we think of it in general, you say it's about laws. So
I mean, we can think that quantum mechanics is a change in law of probability. I mean, we take.
Are you answering what makes it different, or
Yeah,
what is it about?
What makes it different?
Oh, different. Okay. So it's a different law.
Different law of probability.
Law of probability. Okay. That's not too far what I'm trying to say with the term quantum measure theory. So what about someone else? What is quantum mechanics about? Yeah.
The dynamics of a macroscopic domain.
Okay, so it's about the microscopic domain. So it's the dynamics of the microscope. Let's take one or two more. Yeah. The dynamic. So okay, so that's a very traditional, in some sense. So it's the dynamics of operator observables. So you presumably have something like the Heisenberg picture in mind when you say it this way, not the Schrödinger picture. Okay, let's take one more. And what makes quantum mechanics different? Well, I suppose we see the answer here, but maybe is your answer that it's different because it deals with operators, or why is it different from classical? No, let's finish this. So what makes it different is that it's stochastic as opposed to deterministic. One more, what? Uncertainty? Sorry, what? And simultaneous measurements, okay. So that's it's another thing that makes it different. And that'll be the last one. Very quickly then. What makes it different is that we can't know it puts limits on what we can know. Limits knowledge. Yeah, so all of these are good, important. It limits our knowledge. And then the absolute last one. Who was it? Yeah. Okay. This is related to this. It's a limited, fundamental limits on precision instead of just practical limits on precision. Okay, so let me now list possible answers that one could give. Some of them were given here. Some of the answers were different. So when I say what is it about, there's sort of two general classes of operators. I think in the way I asked it, it was a little vague, but I like the answer. It is about microscopic dynamics, hopefully about dynamics in general. It's about the world in general, if you like. But if we narrow it down a little bit, we can say what I was really thinking of is the question, is it about the wave function? No one gave that answer. But someone did give the answer that it's about operators. Is it basically dealing with operators, or is it dealing with histories? So the idea, when I say history, I hope everyone knows roughly what I'm talking about, like a trajectory of a particle or a field configuration, whatever classically would have defined the reality. So the history's approach would give this answer and not this answer. Is it also about momentary states, which is what momentary, the thing to be stressed here is momentary states, or is it about whole space-time global events, which I'll call here processes? Again, this is the history's approach. This is the kind of answer that the history approach would give. It's about processes, not about instantaneous states. Is it about measurements or events? In other words, processes that really happen, or just things that we can ascertain in a laboratory in our apparatus. And then finally, again, all these are the kind of answered, this is the kind of thinking that leads to the history's way of formulating quantum mechanics. And then finally, what does it generalize? I said that before. On one hand, if you look at a textbook in quantum mechanics, I don't know, 80%, 90%, 95%, you're going to see a little chapter on Hamiltonian mechanics coming first. You're not going to see a chapter on random walks or Brownian motion or the Wiener process, but I want to say that they should have such a chapter if they were trying to work with the path integral and not put it in some little sort of chapter that you can skip over, chapter 15 or something like that. And then the final thing is, what is the key difference if you, of course, there's a whole bunch of answers, and the answers I'm suggesting here have only partly overlapped what people suggested. But to see the contrast between the two views, the traditional view would probably be the superposition principle is what's different. It tells us how from states you can form new states in a way that's not possible classically. If you're thinking of operators, you would say it's the non-commutativity of the operators, PQ minus QP. This is my symbol for commutativity. So I won't use it again, but that's why I've written it here. So it's a symbol to mean AB equals BA. That's not important. Or is it about, and this is again the answer on the history side, it's about interference, that different processes, different events, macroscopic, different space-time possibilities, different alternative ways of some event happening, they can interfere with each other. And this, of course, has a very precise mathematical sense, which we'll see. Okay. So let me, I could ask for questions, but I think this is too general. I don't think it requires questions. But but if someone has a question, anyway, I'll stop. So let me now give an example of more precise, what I mean by an event and what I mean by a history in relation to this, in relation to this example called the two-site hopper. So what is this? I started to draw it over here. You can think of it as a kind of space-time lattice. Just think of it's a generalization, or very simple. It's an anti-generalization, whatever that is. A simplification, specialization of something like the Hubbard model, where you have a particle hopping on a lattice. And this lattice has only two nodes, and the particle, and furthermore, time is discrete, whereas in something like Hubbard model, it's continuous. Time will be discrete, as it is in the random walk. And all that happened, what is a history, is that the particle, we can give these names 0 and 1. Say the particle, say we started off as an initial condition always at 0. It can, for example, stay at 0, then hop to 1 at the next time, then stay at 1, and then hop back to 0, then hop to 1, and so on. So that's a history. That's all I mean by a history, and I'll give it, I'll almost always, if not always, use the symbol gamma for the history. It's a kind of trajectory. If I want to give it, if I want to express it in symbols, I can just give the list of the locations that the particle was at. So in this case, it was 0, then it always starts at 0, then it was 0 again, then it was at 1, then it was 1, then it was 0, 1. And it could go on forever. Or if I stop at a finite time, which I always will to make everything finite, then this will be a finite string. So history can be represented as a bit string in this particular case. Okay, so I hope that's the idea of a history. If we're dealing with a more complicated theory like field theory, then history is something much more complicated. But if we saw it as a latticized field theory, like a field living on a causal set, then history would be a value of the scalar field. Say it's a scalar field, a number for every point of space-time or every element of the causal set in the causal set case. So that's the history. It's the thing that enters into the path integral, which is also called sum over histories. Now what's in it? So that's the idea of history. The other key idea is the idea, and I'll come back to this, but I'll usually, the space of all histories I'll call omega. If it's all histories of length n, I'll call it omega of n. Then the other key idea, or in some sense even more key, is the idea of event. An event is a set, well, let me say, the mathematical definition is simple. An event is a set of histories. But why do we use that language? On the one hand, because this is the language of classical probability theory, stochastic processes, a measurable subset of the history space, which they call the sample space usually, is an event. It also is exactly, if you think about it, and I leave it to you to think about it, if you think about it, that an event, in everyday language, an event actually is a set of histories. So I'll give a couple of examples. Here, I'll usually use symbols like E or A or B, capital Roman letters for histories. So here, let me consider an event. So we run this for a certain time, n, and we can ask, did the particle, it started at 0, we can ask, did it spend more time at 0 or more time at 1? Spending more time at 0 is an event. Spending more time at 1 is a complementary event. Unless there's a tie, then they're not quite complements. Let's say it's an odd number of times so that it never ties. So spending more time at 0 is an event. And when I say it's a history, let me make it precise, for times up to 5. Otherwise, if we let it go forever, then it's not a well-defined. It's infinity versus infinity in general. Let's say we stop it. So suppose we take this n to be 5, and we say that we ask whether in the first 5 moments it spends more time at 0 or more time at 1. And what would be an example? I'm usually going to write a history as a bit string like this, whatever these square brackets around it. So what's an example of a history that belongs to E? Well, consider 0, 1, 0, 0, 1. 1, 2, 3, 4. So there's 3 zeros here and 2 1s. So it spends more time at 0. So it does belong to the event E. On the other hand, something else, 0, 1, 1, 1, 0, for example, it spends more time at 1 than 0, so that doesn't belong to E. In fact, what it belongs to is the complementary event, which you can write as this, complement, the set of all histories in omega that are not in E using that notation. the thing that I want to stress, I'll give another example in a second, which will be the one we'll deal with when we come to the random walk in a moment. But the second thing, the thing I want to stress at this point is, notice that this event refers to no single time. If you know everything about what happens at times 3, you just don't know whether the particle spent more time at 0 or more time at 1. It refers, it's one of these what I call events distributed in time, for which I'm still looking for a better name. And the other thing is that there's no, if we think of this as a quantum process, which we will, there's no obvious, so let me just, maybe should I write these down? These are somehow the key points of what I'm trying to convey. No, so I'll harp on them if I can remember to do so. It refers to no single time, and it corresponds to no obvious measurement. I mean, that's too small, but it says no obvious measurement. How would you design a device that would ask whether the particle spent more time at 0 than at 1? That's what we're going to do at the end, at the culmination of the lecture. Yeah. That's right. We're not doing quantum field theory here or something. It's not second quantum. It's just a classical, I mean, what shall I call it? Non-relativistic, if you like. Yeah, the particle cannot go back in time. So if I've made it go back in time like this, then it would be as, you know, in another language, there would have been 2 particles here, and then they merged and annihilated or something like that. They scattered, so that would be more like quantum field theory, second quantized theory of the particle. Is there another question? Oh, thank you for asking. I always forget to say that. There's another usage of the word event, which just means point of space-time. You could think of that as a very, very special case of this, if you think of the point being there as something actually happening. But otherwise, it's completely different terminology. So event does not mean point of, it does not mean point of space-time. It means a set of histories. Yes, exactly. Yeah, you have to take all the gammas and all the times at which those gammas are. Yes, each of these is that's right. It's a point of space and time, if you like. We're dealing with a kind of discrete space-time. Yeah. Okay, so. Yes, the event is not linked to a moment of time. That's right. That's somehow the main. And there's no moment of time that you could point to and say, at this moment the event happened or it didn't happen. Yeah, no, let me not answer that. Well, what I have in mind is a kind of way of thinking of space-time which is inspired by causal sets, in which space-time is constituted by a growth process. And the event in that case would be the birth of that element of the causal set, or in the continuum, it's a little hard to visualize what it really means, but it would be the birth of that point of space-time. So let me not say more than that. But you're right, it's in no way obvious why I said that that other usage is a special case of this. But that's what I had in mind. For the purpose of this discussion, this lecture, let's just say that they're 2 totally different usages of the word event. So what I want to do now is play around with some of these concepts in a very familiar setting, and that of probability theory, of a classical system, and then point out in the next step, I feel this keeps getting louder and softer, but I'm not. Then point out, is that better or worse? Is that better? No. Yeah? Oh, only for simplicity. This is the simplest example. In fact, when we're now going to discuss the classical random walk, and in that case, it's a walk on the integers. So now it'll be, a trajectory will be a sequence of integers rather than. Yeah, that's right, yes, that's right. So you can identify, it's very, in fact, there's a paper that Stan Gutter and I wrote about this on the two-side hopper. And he likes very much that notation. So you can actually represent an event as a binary, as a number in binary notation. And even if you let the time run to infinity, it's a binary decimal, if that's not a contradiction in terms. It's a binary fraction between 0 and 1. You could, well, the whole trajectory you could consider as a point in this particular case, as a point of the line. Is that what you mean? Yes. Yeah, that would be a mathematically equivalent, but it wouldn't be physically appropriate. But it does make them, I mean, it is a convenient mathematical device to talk about, in a simple way to talk about the general trajectory. Oh, no, well, yes, when I come to the random, here I've allowed it to stay, it has two choices, hop or not hop. When we come to the random walk, the simplest version of that, it has no choice to stay put. So at every step, it either moves to the right or it moves to the left. Is that what you're saying? Yes. Say it again? I didn't get the...
Generalized way, right? Sorry.
Yes.
So why not include the possibilities that at a particular instant of time, say you're considering this time slice, as the second one. So you could have gone from that at the time t2. You could have gone from the 0, the 2, say 1, the t1. You could have gone from the 0 side to one side rather than going in the t equal to 2 from. I mean,
I don't know. I really don't. Are you asking me to put other points here in between?
Can I go?
Or are you just saying that there might be
I'm
another
saying about the parallel line. I mean,
here's another trajectory. I don't know if this is what you're saying.
Not like that.
So we can go put this off. I just haven't understand the question. But if you're asking me to put other points in this, no.
Yeah, time scale.
Oh, it's just a way. Oh, I see what you mean. I could represent. I don't have to draw lines. Is that?
No.
I could represent a trajectory just by coloring.
So
in the dots, I could represent this trajectory by this.
Yeah, that's not.
That's
no, that's not the question. Question is.
Oh, time is running.
Yeah,
time
I mean,
is like this. It's a space-time by
the question is about. Can we allow the possibility of transition to 1 to 0 at a particular time?
No, This is time. This is discrete time. This, if you like, this is the whole of, as someone said, in this simplified model.
No, but the way we define the event, it's still
different.
different.
Wait a minute. Space-time in this model is no more than this set, this lattice. That's it. There's no question of when does it go from 0 to 1. If it's at 0 and then at the next moment it's at 1, that's when it went from 0 to 1. It's not that it could wait a little longer and then go from 0 to 1. That has no meaning. This is just a simplification of a world line that you might draw in space-time in a continuum case. Right? that looks like this. If you're familiar with some of the technical ways of making sense, precise mathematical sense of a path integral, then it's very traditional to do what people call latticizing time, and then taking some limit in which the lattice time spacing goes to 0. You could think of this, if you like, as doing that and not taking the limit. But, okay, but time, the idea is that both space and time are discrete in this model. Yeah. It's not, well, what time, well, here I gave you an event. What time is it linked to? Yeah, it's on. Seems to be on. It is on.
Oh, I'm saying that I can give you an example that the event is that the particle at an instance is at 0 position.
Oh, yes. Okay, I'm not saying that every event is what I'm calling distributed in time. There are plenty of events that are linked to a moment of time. For example, the one that you just said, that at time 3, the particle was at position 1. That is an event that is linked to a moment of time, and that is the kind of event that ordinary quantum mechanics usually deals with. Ordinary quantum mechanics ordinarily deals with that kind of event. You ask questions like, you solve the Schrödinger equation, and you ask, what's the probability that I'll find the particle in this region of space at this time? That is an event. I don't mean to exclude those. I'm saying that the interesting event, the ones that make quantum measure theory go beyond ordinary quantum mechanics, are this more general kind of event. So that's why I gave an example of that kind of event here. But definitely those other events exist. Yes? Yes, that is how you should think of it as that. That is exactly what it is. It's a world line in discrete space-time.
Okay, so there are also concepts of, space-like interval, time-like interval.
No, yeah, but here it's, yes, if you like, but the causal structure here is just too simple. So in this case, let's take this element of this discrete space-time. Everything at the later time is to its future, everything at an earlier time is to its past, and only this other simultaneous node at that same time is space-like to it. So it has a very simple, if you like, causal structure. But yeah, you could talk about the causal structure, and that would be manifest in what kind of paths are possible. The fact that I don't draw a path that goes from here to here would be related to the fact that we're not thinking of these as causally related. But I'm not trying to do anything fancy. I'm just trying to do, you can think of this non-relativistically any way you like. I'm just trying to set up a simple quantum system in which the notions of path integral make sense, and we'll be able to do complete calculations. Okay? Okay. Well, I'm, as usual, getting behind already, so I'm tempted. I'm tempted to skip the random walk, but let me try. Maybe it's the worst compromise, but let me try to sort of rush through the random walk and at least summarize the things. Other people had the same. Yeah. Let me deterministically go through the random walk example, because it's kind of pretty, although some of the beauty, I think, will be lost if I can't show the proofs, which are really very pretty proofs. But you can find it in many, well, for example, there's a textbook by Feller in which this is all discussed, although not quite in a physicist's language, unfortunately. So this is problem of arrival time. Some of you who know something about, or read or heard something about the, oh, Feller, yeah. I don't know, but I don't know the name, but it's probably, I'm sure it has the words probability theory in it somewhere. So you could find an account of that. So, so now we're dealing with something very like this, but now it's on the integers. So a trajectory, it starts, say, at 0. So it starts at, again, I'll use the tx notation. I should have said that, but it's so sort of ingrained in me that I didn't bother to say it. So time comes first and then position. And now the effective space-time that we're dealing with is this integer lattice so if you like, two-dimensional Minkowski space, but it's nothing to do with Minkowski space. It's just an integer lattice. So the particle starts at 0. I won't write it out, but a trajectory now, I'll try and draw something. A trajectory now is a sequence again. Now, oh, but the rules have changed a little bit now. This is a traditional random walk. It's sometimes called the drunkard's walk. So they're not very steady. They can't stand still, so they either something like that. So at each moment of time, they take a step, either to the right or the left. So here, a trajectory could be like this, and so on. So that's a particular history of the drunk or of the random walk. So it starts, as I said, we could think of the lattice on which it's moving from a space-time point of view, z squared or z cross z, just given by a location. A node in this is given by two integers, the time and the space, both of which are discrete. We'll always, for simplicity, well, actually we won't, so I shouldn't say that. But in this one that I drew, I've started it at the origin at 0, 0. And the question is, we want to find the probability to reach, so our event here is that it reaches it reaches the node TB for the first time. So here, assuming it started at 0 now, it reaches this for the first time at t. Maybe it's not said very grammatically, but you can see what I mean. We're interested in the event that the particle reaches, having started at 0, it reaches x equals b, and at time t, and it never reached there at an earlier time. So that's in the language of stochastic processes. It's called, in physics, physicists would tend to say arrival time. It's called, I think, if you look in Feller, for example, I think you'll see it called first passage question. All we want to do is compute the probability of this. So I'm going to rush, as I said, rush through the results by just stating a series of 2 or 3 lemmas, which I was intending to actually show the proof, or part of the proof, and make part of the proof homework, but I'm now going to make the whole proof homework. So let me introduce some notation. Let A and B be points of space-time, of this latticized space-time. So that's in Z2, that's squared. So I use this notation. That means that the path gamma joins A to B. Okay. And where A I'll take to be some initial time and initial location, and B I'll take some T final and final X final location. And I need one more notation, which is this proof actually uses, although you won't find those words probably in Feller, it uses the notion of time reversal, parity transformation and translation, if you like. So it's just another notation when I write, if I write A prime, well, if I have a node and I prime it, that's just parity. So I'm copying Feller's notation. So it's T minus X instead of Tx. Okay. So that's parity. So here's the series of lemmas. So the first lemma, maybe I'll say in words how the proof goes, but I'll leave the actual details. So, so I need to write another, I need another definition as well. So in this case, I'll write, this is an obvious definition, for a path joining A to B, initial time, initial position, final position, I'll write delta T as T final minus T initial, and delta X, of course, is X final minus X initial, right? Then, here's the lemma. One thing I didn't say that I should have said is that this is an unbiased random walk. Right? So it's not that the person is leaning more to the right or something like that. So the probability of each step is equal to the right and the left probability of a half. So therefore, if you want to compute the probability of any event, an event is just a set of trajectories, a set of histories. All the histories separately have the same probability because they're just a sequence of steps, each of which had probability a half. So to compute the probability of a given event is the same thing as just counting the number of histories making up that event. And then just dividing through by 2 to the n, which is the total number of histories that there could have been in that time. Okay, so here's the lemma. So we consider this gamma here, and with this notation, the number of paths gamma going from A to B initial is equal to delta T, but this is a binomial coefficient, delta X over 2. Okay. So the picture here, if you like, is delta T, and there's sort of delta X, and there's the path, something like this. This is B and this is A. We're just counting the total number of paths going from A to B, and the claim is that it's given by this binomial coefficient. Everyone knows this notation for the binomial coefficient. Right? Yes. No? Yes. Okay. The way to prove it is just to figure out that if it moves a distance delta, net distance delta x, that the number, you can introduce the number of positive steps and the plus and the number of negative steps minus, then you know that then, well, here I'm writing it out. The total number of steps is delta t, and the net displacement is the number of positive minus negative steps, that's delta x. Solve those equations for plus steps and minus steps. Notice that the plus steps can be chosen anywhere within the delta t, any choice of those number of those particular moments where it moves in a positive direction. And you got this binomial coefficient. You can leave that as a homework. This H means homework. The second thing is lemma. Second lemma, this is the more interesting, more tricky. It's called the reflection principle. Sometimes it's called the method of image charges. And what it tells you is consider two classes of paths. You consider A and B to the, this is x equals 0. You have A and B. You consider all paths that go from A to B remain to the right, but touch the origin. And now the claim is that the number of paths, which are, I'll just write positive, but touch x equals 0, that equals the number of all paths from A prime to B, where A prime is the reflection, the parity reflection of A. See if I can draw this. I can't do it, but anyway, I wanted this to be the mirror image of this. So this is A prime. And the proof, it's actually, the proof is geometrically obvious, and again, I'll leave it to you to verify that it really is what I'm saying. But the reason you can see in this picture that you would see it better if I made this actually touch the origin. Then there'll be a first moment at which it touches the origin. We require that it does touch the origin. And then I just take that and reflect that initial segment of the path to the left, and I'll get a path from A prime to B. Any path from A prime to B must cross the origin. So if you think it through, there's a one-to-one correspondence, a bijection between the first set of paths and the second set of paths. And then from these, we'll prove a theorem, a theorem and a corollary. And the corollary will give us the answer to that we're seeking, the total number of paths that start at the origin and arrive at TB for the first, at position B for the first time at time t. So the theorem is the number of strictly positive paths, gamma, from the 0, 0 to t, capital TB, I made t capital number here, is remarkably similar to the expression we wrote before, just with a prefactor of b over t. Right? It's t choose b plus t over 2. So this is the binomial coefficient, t, b plus t over 2, and there's a b over t in front. This is the one that I wanted to give a little more detail in the proof, but since I'm getting so far behind already, as could have been predicted, since I'm getting so far behind, I'm going to leave it to you. But let me just indicate, so this is another homework. Let me draw a picture for it. Now, so for this theorem, can people still see this? It's supposed to start at the origin. It's supposed to arrive up here at TB, T comma B, without ever remaining strictly positive, without ever touching the origin. So what does that mean? The first step, it can either go to the left or if it goes to the right. If it goes to the left, then we're dead already. It's not in that step. So it has to go to the right, the first step. So all such paths, so this is the event. So if gamma is in this event that I've just defined, let's call it event T sub B, then how can I say gamma? Let's just say the point 1, 1 is part of the world line gamma. It must go through 1, 1. So if I ask for the total number of paths that go from in this event from the origin to here without ever coming back to the origin, it's the same thing as the total number of paths that go from 1 to TB without ever coming back to the origin. You can write this as the difference between the total number, I'll say just in words, you can write this as the difference between all the paths that go from 1, 1 to TB, taking away all those which touch the, and remain weakly positive, and take away all those which touch the origin. So you get it as the difference of two things computed in the previous lemmas, and you use a little bit of binomial coefficient manipulation, basically trivial, and you get this result, which I've stated here. Okay, and then the last thing is a corollary. which is, this is also, it's the same number that, well, that belong to the event that we're interested in. First arrival, I'll just say for short, first arrival at t comma b, which I defined before what we meant by that. And then again, the picture, oh, I forgot to fill in the past. So the picture, these are the class of paths we're talking about. If you look at, this is what we counted in the theorem, but now in the corollary, just look at this picture, apply time reversal and translate it so that this becomes at the origin. You should be able to see that this is a path that began at, now time is running backwards, but doesn't affect the counting. You should be able to see that this began at the origin, arrived for the first time at the origin, which has now been translated to b. So it moved a distance b for the first time at this time t. If it had arrived sooner, it would have touched the origin earlier. It wouldn't be strictly positive. Anyway, so I just leave it. I don't expect you to follow it in detail, but if you think about it, it's really very simple and obvious that this is true. So I'll leave this for homework. So the important point, which I always try to keep stressing, is that the answer to this number which we've produced, is not coded into the value of evolving probability density at any time. You know, you can define a sort of rho of t, rho sub t of x. This is the analog of the Schrödinger equation for this theorem. What's the probability of density for finding it at x at a given time t? This is kind of the analog of psi Schrödinger t. It starts off as a delta function. Because the particle starts at the origin, and then it gets broader and broader. And as is well known, in the limit, this is the central limit theorem, a very large time that looks roughly like a Gaussian. But knowing it for every time, this just doesn't give you the answer to this question. You have to deal with the paths in their space-time aspect. You have to deal. So this is what I was calling an event distributed in time, and we don't get it from the propagate. That's the main moral. So let me, and now one thing we want to take away from this, going for quantum measure theory, is that, what did we really do? Actually, maybe I should say this. I said it in words, but maybe I should write it. When we want to convert this to a probability, we have to put it 1/2 to the n. So the probability of this arrival event, I'll just call it arrival event, is the same number, b over t. T choose b plus t over 2. By the way, you can convince yourself this is always an integer. Time divided by the total number of paths in time t, which is 2 to the t, so we'd have a factor of 1/2 to the t. So when we take normalization into account, this is the probability, not just the number of paths. So the one thing that I want to take away from this, just think what we really did. We wanted to get the probability of a certain event, this arrival event, first passage event. We did it by getting noticing the probability of each history. That event is a set of histories. We found the probability of each history, which was 1/2 to the t in this case, and because we ran the process for time t only, and then we just added up the probability. In other words, what we used was the probability of gamma, which in this case was 1/2. And we used, this is the key thing, we used the formula that the probability of any event is equal to just, this is all, in some sense, this is all, from a mathematical point of view, this is all that classical probability theory is. It's just that the probability of any event is nothing but the sum of the probabilities of the constituent histories that make up that event. The whole rest of probability theory is just mathematical games to try and compute this sum for interesting events, plus a whole bunch of technical complications that you hit when you try to consider infinite history space, like letting time run to infinity, or having a continuum of paths that make this formula would then become meaningless because each individual path would have probability 0, and you'd be taking an infinite sum, 0 plus 0. So there's a lot of technical issues, but conceptually this formula is the whole classical probability. You attribute to each history a probability, and to each event we attribute a measure, or a probability measure as it's called, which is just the sum of the probabilities or measures of the individual histories making up that event. Now I've got sort of lost. Where is this? That's it. So quantum mechanics is going to be exactly like this, except another term is coming in here that represents interference. So let me jump ahead and write it down and then say a little bit. At least, hopefully I can get far enough. I don't think I'm going to get to the axioms right now, but I guess this afternoon. So what quantum mechanics will add is a sum of interference terms. So gamma, it's now a double sum over pairs of histories in E, not equal to each other. And it's another term which I'll call I of gamma prime. The interference between gamma and gamma prime. That's the whole difference in a mathematical level between quantum measure theory, the path integral, or generalized path integral, if you like, for quantum mechanics, and classical probability theory. The whole point is now to say what, of course, to get any particular theory, you want to say what are this mu of gamma and what is this I? And that'll be done in terms of, in a unitary theory, or in general, under these axioms, in terms of something that's called the decoherence function. So let me make a start, since we have a few minutes. Let me make a start on describing this whole framework. Oh, and what I wanted to say also is that, I'll say this again, but notice that there's no, I might have added more terms that involved triples of events. That would be higher order interference. It's not there in quantum mechanics, and that's what's in some sense responsible for, or equivalent to, the Born rule, in a way that'll be familiar to some people, but not yet everyone. And which has been tested in a series of very nice experiments, pioneered originally by Urbashi. And I think is Gregor Weiss coming here next week, so he also, and now originally in Waterloo, and then many people doing variations and improvements on the theory, and even corrections to the theory. That's the other work, Gallery Bidden, or wherever it is currently located. So, so let me just make a little start on, start here. So tell me when, yeah. current state of understanding is you can stop here. So we recently had people are thinking seriously about this, both in the experimental way to see whether you can detect the presence of such terms, and also theoretically, can we design full dynamical theories in which this kind of higher order term would arise. So I suppose it's online. There was recently a conference at Perimeter devoted to the possibility of higher order interference. I think all those talks will be online. The only one that won't be online was my introductory talk for some reason, because it was an introduction. Anyway, but everything is, aside from that, I think was online. So what I want to now further introduce is what I call histories-based quantum theory, quantum mechanics, which for short is called quantum measure theory, because the dynamical laws are coded into some generalization of the classical probability measure. So, as I said, I think just before, I don't know why this, it's not a problem that it keeps going louder and softer. Maybe that'll work better, we'll see. Because, as I said, because of interference, and we'll see this explicitly in a nice example, because of interference, mu takes a more general form. But the only change is in that. So if we ask what happens in the transition from the classical stochastic process to the quantum case, we can discuss this in two levels, the dynamical level and the kinematic level. I use this in the way that it's used in physics, especially in very old physics textbooks. You'll see kinematics is sometimes described as the description of motion, and dynamics is the laws of motion or the forces that cause them. I don't know what they say in those books, but the important thing is that kinematics is kind of what are we talking about? It's what a philosopher would call it maybe the ontology of this theory. But I think kinematics is a much nicer, more venerable word for physicists. And then there's the dynamics, which is the laws of motion. Kinematics gives us all the possibilities that there might be, all the possible trajectories, but dynamics tells us which trajectories really will happen, or which are more likely, or something like that. And in this case, it'll tell us which events have a greater measure and which events have a smaller measure. So, as we just saw in a little bit of detail, not as much as I was hoping, but in the case of the random walk, we saw an explicit example where the kinematics was just a set of trajectories, a set of histories, and I called omega the space of all histories. This is the same, exactly the same in the case of quantum measures. What changes is the dynamics. So mu now is not just a simple sum like that. It has interference terms. But if you say, where did these interference terms really come from? They come from the path integral, or if I say it in a somewhat more general way, they come from the fact that the quantum formalism, in a histories way, the path integral, it deals with amplitudes and not directly with probabilities. And when we do compute probabilities, they're squares of amplitudes, or more precisely, as we'll see, sums of squares of sums of amplitudes. That's the general form of the quantum measure. The thing that that doesn't occur here is the Schrödinger equation. And we won't ever mention it. We won't need observable operators. Either in Schrödinger or Heisenberg picture. We won't have a Hilbert space of states. We won't have any of that stuff, although some of that stuff can be recovered, but it won't be a fundamental input to the theory. And the slogan of this, or my claim, is, I've stated it in slightly exaggerated form, anything you can compute, that is anything quantum mechanics can compute, the path integral can compute. I said it sort of in words before without writing it, I think, what I meant, and I'll say that again, because I think that's an absolutely key point. It shows the sense in which it is possible to have a self-contained history's formulation of quantum mechanics. It's just not the way people talk. They usually talk about the path integral as something to compute propagators. Basically, they talk about the path integral as a mathematical device for solving the Schrödinger equation. But it's, from this point of view, it's actually much more. It's really at the center, the heart of quantum dynamics. Okay, so I think I'm almost out of time. We hadn't started a little late. I would be out of time. I'll take a couple of more minutes to just to telegraph what we'll do next. So what I want to do next is, so this was all kind of abstract, although I think it's to some extent familiar. I want to bring it down to earth as much as possible. So I'm going to recall how the path integral works. Particular case, which is that of the particular Mach-Zehnder pattern interferometer. We'll just go through it carefully and compute the amplitudes and the quantum measure for a couple of interesting classes, a couple of interesting events. It will also although in this set of lectures, I will not dwell very much on this, but it will illustrate the idea of preclusion, which is events that have zero measure. And one can take as a fundamental postulate that events which have zero measure don't happen. And that leads, well, there's a lot of interesting conclusions from this. In fact, most of the, let's say half the paradoxes of quantum mechanics that makes it so hard to think about quantum world as one does the classical world come from the fact that certain events are precluded, too many events are precluded, and that blocks the classical picture. This shows up in this three-slit or three-box example, which you've already heard about, I think, in very similar language to what I will use. I may just skip it, but if at the end there's time, which I seriously doubt, but if at the end there is time, I may come back and show it, because it also makes a nice illustration. But I won't, here I just want to focus on the computation of the quantum measure for various events. And then I'll show you the form of the quantum measure for a general unitary theory. Sort of simplified, so general you can put in quotes. But basically you got the general form, and then we'll talk about some axioms for quantum measure theory, expressed in terms of what's called the decoherence function, which assigns a complex number to every pair of events. This is the name is given to it by Jim Hartle and Murray Gell-Mann. Give axioms for this, and might as well say now, the relation between the decoherence functional, this is a complex number, decoherence function. The relation between that and the quantum measure of an event is that the measure of the event is nothing but decoherence functional, sort of diagonal value of the decoherence function. So I'll write down those axioms. And then, I guess, then we'll start looking at how to mention how it implies the Born rule, and then we'll look at how we can design an experiment to actually reveal in the laboratory the value of mu of E for any event E, especially, most especially, for these events which I've called distributed in time. That seems a good place to break. Any questions? No. Was there? Yeah. Yes, this will be the path integral that you usually see is used to produce a propagator, and it's what I would call a single path integral. So you just perform a sum over all paths, say from A to B or something like that. That gives you a complex number, but it doesn't give you yet this quantum measure. If you want if you want to get a probability out, you would have to square that amplitude. When you square, so now you'll have a product of the complex numbers coming from the first set of paths, there's the complex numbers coming from the second set of paths. You can write that as a sum of products over pairs of paths. And that's really all that's going on in computing mu of E. So mu of E takes the form of a double path integral. So the usual thing, call it the single path integral. And then this quantum measure theory is dealing with a double path integral. And I'll give you the exact form of that double path integral. It takes into account specifically which histories do interfere and which histories do not interfere. That's a crucial point. So you won't see, if you just think of it, what you were talking about here, paths going from A to B. Because it turns out that in quantum mechanics, paths which terminate at the same point can interfere. Paths which terminate at different points do not interfere. That has to be built into the expression for the double path integral. You'll see what it means. Well, you're familiar with it. When you say that they're interfering from the point of view of the path integral, it means that you add their amplitudes and then square. When they don't interfere, it means you square the amplitudes and then add. So you're familiar with this, like if you want to compute, say, scattering amplitude, scattering probability across section. You know, there's the so-called inclusive cross section. That means the particle could come out with any one of a number of momenta. If you want the total probability, you don't add the amplitude for each momentum and then square it. You say for each momentum, you add the amplitudes that lead to that momentum. You square that, and then you sum over the separate momentum. So that's what I mean. So it's the difference between adding and then squaring, or squaring and then adding. The second one I call not interfering, and the first one I call interfering. The first one will lead to terms like this, or was it the second one? And the ones where you add the amplitudes and then square will lead to terms like this, or the ones where you square and then add the amplitudes will not lead to terms like this.
So if there are no questions, let's thank Professor Sorkin and let's break for the